We now begin a new section of the course on Einstein and the quantum. We'll proceed in 3 steps along the way in this lecture. The first is the radical idea that Einstein had about quantizing light, coming back to early on in the course. Second, we'll look at Heisenberg and Schrödinger's ferocious battle for a way of formulating the new quantum mechanics. And third, we'll look at the epic struggle between Einstein and Bohr. If there's one thing I want to have come across in this discussion of Einstein and the quantum, which we'll talk about today and then in 2 subsequent lectures, is that Einstein was not against quantum mechanics. Although it's said a million times, and it'll be said a million times in the future by people, Einstein was one of the inventors of the quantum theory of nature, and his objection was to the idea that quantum mechanics was a complete theory. He thought it didn't go far enough. He thought it could be brought to a completion that would satisfy his detailed representation of nature in the way he wanted. Let's go back to Einstein in mid-May of 1905. This was the moment when he was formulating his paper on special relativity. And he writes to his friend Conrad Habicht, one of the co-founders of the Olympia Academy, this group of cheese and wine eating, rather impoverished students. And here's what he said. "So what are you up to, you frozen whale, you smoked, dried, canned piece of soul, or whatever else I would like to hurl at your head? Why haven't you sent your dissertation? I promise you 4 papers in return, the first of which I might send you soon. The paper deals with radiation and the energy properties of light and is very revolutionary." Then he talks about atomic size in his paper on Brownian motion. The 4th paper is only a rough draft at this point and is in electrodynamics of moving bodies, which employs a modification of the theory of space and time. But the paper that Einstein singled out as very revolutionary was not special relativity. It was the idea that light comes in chunks, traveling almost as if particles through the world. This was very revolutionary, totally unexpected, totally unfamiliar. Einstein's idea of Brownian motion, as we saw, was almost immediately taken up by people at the time. It was an experimentalist's dream subject. You could use little glass beads to study the motion of suspended particles and so on. Special relativity was difficult to understand, but fell into a tradition of thinking about space and time, different frames of reference, electrodynamics. But the idea that the wave theory of light was going to be supplemented, complemented, or displaced by a particulate theory of light, that really sounded wild to people. Some 5 years later, in March of 1910, one of the great physical chemists of the time, Walter Nernst, talked about Einstein and said this: "I believe that as regards the development of physics, we can be very happy to have such an original young thinker, a Boltzmann redivivus. The same certainty and speed of thought, great boldness in theory, which, however, cannot harm, since the most intimate contact with experiment is preserved. Einstein's quantum hypothesis is probably among the most remarkable thought constructions ever. If it is correct, then it indicates completely new paths for the ether and molecular theories. If it is not, it will be a beautiful memory for all times." Einstein was connected to the physical chemist Nernst, and Nernst was connected to Solvay, a hugely successful industrialist who had perfected a way of synthesizing soda ash, sodium carbonate, which was used to soften water and for making glass, for all sorts of things in the industrial world, and he had found a way of combining limestone, salt, and ammonia to do this. He made boatloads of money and used it to support physics and politics and the investigation of a kind of individualist politics and technically based theories of nutrition, scientific production, sociology, But among these tasks was gathering the greatest scientists of the world and putting them to work on some of the problems that they saw as being at the front line of knowledge. Nernst wrote to Solvay in July of 1910 to say, "It would appear that we currently find ourselves in the midst of a new revolution in the principles on which the kinetic theory of matter is based. As has been shown, most notably by Planck and Einstein, contradictions are eliminated if the postulate of quanta of energy is imposed on the notion of electrons and atoms. It unquestionably means a radical reform of current fundamental theories." Well, Solvay was fascinated by this, and they began in 1911 to assemble a rather secretive meeting of a tradition of meetings that became extremely important in the history of physics, which would gather the world's greatest theoretical physicists and some experimentalists to think about what was at the frontiers. Among them was H.A. Lorentz, who was a kind of godfather to theoretical physics. He was the model of what it meant to reason about the ether, and time and space, and matter, electrodynamics. He was a model not only for Einstein, but for Poincaré, for just about everybody. And the question was always at the tip of everyone's tongue when there was a new development in theoretical physics, what does Lorentz think of that? So out of Maxwell's ether theories and all of the swirl of developments that had been developed, Lorentz constantly pressed on the idea of particles and fields, of visualizable particles that could then explain all the phenomena of nature. If light was to be reflected, he pictured a bound electron that would be set in oscillation by an electromagnetic field, and then the electron would re-radiate that light energy in a different direction. If it was refraction, if it was any of the phenomena, even the complicated spectroscopic effects, like the fact that a single line in the spectroscopic image could be split by a magnetic field. And Lorentz found a way of using his particulate electrons and their boundness and how they would move to explain this splitting of the line. So he was a model for all of these developments. He was there. Poincaré was present at this 1911 meeting. Einstein was at the 1911 meeting. And Einstein commented at that first meeting in 1911 that H.A. Lorentz is a marvel of intelligence and tact. He is a living work of art. In my opinion, he was the most intelligent among the theoreticians present. So even though Lorentz gave Einstein something of a hard time about some of his developments, he nonetheless respected Lorentz tremendously. We've seen this interaction back in the period we were talking about relativity. Poincaré, Einstein reported, was simply negative in general, and all his acumen notwithstanding, he showed little grasp of the situation. What particularly caused strife between Poincaré and Einstein was the question of light being broken up into particles. Poincaré said this. He was leading a session in which Einstein's work was being discussed. What the new research seems to put in question is not only the fundamental principles of mechanics, it is something that seems to us up to now inseparable from the very notion of a natural law. Can we still express these laws in the form of differential equations? So Poincaré was trying to understand mechanics, the world, in terms of the continuing and continuous transformation of nature. And differential equations are the way of tracking over time the continuous development of natural phenomena. Poincaré continued, "We just heard a theory based in one place on the principles of the old mechanics, and another on the new hypothesis that are their negation. One should not forget that there's no proposition that one can't easily demonstrate through the use of two contradictory premises." So for Poincaré, there was something lunatic, destructively lunatic about what Einstein was up to. You couldn't have light be a wave and also have light be a particle without running directly not only into a contradiction about the nature of light, but really threatening all of science. At one point, Poincaré, in frustration, said to Einstein, "What mechanics are you using?" And when Einstein replied, "No mechanics," the witness to this exchange said that This seemed to surprise his interlocutor, because Poincaré was willing to change the differential equations, to change the description of nature. What he was not willing to do was to say that the description of nature itself was contradictory. So Poincaré said, at Solvay, before accepting these discontinuities, that is to say the photon, which force the abandonment of our usual expression of natural laws through differential equations, it would be better to try making mass depend not only on speed, but also on acceleration. Einstein and Poincaré's disagreement was not that Einstein was a radical and Poincaré was a conservative. Poincaré was willing to change the laws of physics. He just wanted them to be replaced by other laws that had the form that he could grasp, namely a continuous description through differential equations of how nature would go from one state to subsequent states. After the meeting, Poincaré added this footnote. On my return to Paris, I tried calculations in the direction of changing the theory as I thought might be useful. They led me to a negative result. The hypothesis of quanta appears to be the only one that leads to the experimental law of radiation. So Poincaré reluctantly, fighting it down the road, came to agree with Einstein that you needed to have light described in this quantum way.